So I'll tell you a little bit about recent work with Wyatt Reeves and Moshe Rosali at UBC, and work in progress with Tarek Anus in Amsterdam. And this work is about reparametrization modes, which I will define what I mean by that. And I will provide a way for me to describe certain universal aspects of conformal field theories that have to do with energy momentum, stress energy tensor exchanges, energy momentum conservation, or graviton physics in ADS CFT. So we will see why this is an interesting aspect of conformal field theories that's worth understanding in detail. And this formalism of reparametrization modes has sort of a conceptual and a technical aspect for me. The conceptual aspect is that it gives a useful way to piece together various different ideas that have come up over the last few years. A bit more of that will be on the next slide. So here are a couple different things that sort of seem like they should belong together, and I will provide some sort of framework how you can conceptualize them and think about them in some useful way. And the other aspect of this is just a technical aspect that we will see that this formalism is very useful for certain calculations in conformal field theories. And for some calculations, it's very efficient and allows you to do calculations that are otherwise much harder to do. Okay, here's a rough outline of this talk. I'm going to first explain what I mean by these reparametrization modes. I'll very briefly review the SYK model to set the stage, and then talk about conformal field theories. In the second half of my talk, I will relate this to techniques that are being used to think about conformal blocks in CFTs, and in particular Virasoro blocks in 2D CFTs. And in the end, I have various remarks about thermal states and applications to things like quantum chaos. So let me very briefly remind you of this model of n Majorana fermions that you've probably all seen. And there's only one aspect of this that I want to remind you of, which is that this SYK model at low energies develops a conformal symmetry, which is just reparametrization symmetry. And it has an interesting pattern of symmetry breaking. And in particular, there's some explicit symmetry breaking, which is due to this Schwarzian action. And the Schwarzian action you can think of as an effective field theory for this reparametrization goldstone, or for this reparametrization mode f of tau. And this action describes the dominant effects which are associated with the energy mode in this model. And one example for things you can compute with this is an out-of-time order correlation function, which has an enhanced contribution in beta j, where j was the SYK coupling, that grows exponentially in time. So, oops. So the Schwarzian theory was pointed out to be hydrodynamic in the sense that it's a theory of energy conservation. And the question has come up in this paper, among others, whether this Lyapunov growth in out-of-time order correlation functions can more generally be thought of in terms of some effective field theory of
more generally being in higher dimensions.
In particular in higher dimensions, or in other models. So the proposal here in this paper was that, at least for maximally chaotic theories, you can always write down some theory that looks hydrodynamic, in the sense that it's a theory of energy conservation, and that this theory would capture maximal chaos. I'll be a little bit more specific towards the end of my talk. But
has something to do here with the fact that the model is not exactly conform, but in higher dimensions.
yes, there will be differences. Okay, I should say one more thing. The proposal here was not just about higher dimensions, but also about theories that are not necessarily conformal. That was a very general proposal, and we will have some comments in the end about how far you can maybe take that or not. But this is sort of the effective field theory motivation for thinking about this. That there seems to be, at least to some extent, a way in which you can understand this Lyapunov growth in terms of some effective field theory. And I'll make this a little bit more precise now for two-dimensional conformal field theories. So consider some two-dimensional conformal field theory at finite temperature, and more assumptions will be implicit for this to be sensible or useful. So I'll consider the central charge to be large, and the CFT should not be integrable, and it should have a Cardi-like spectrum, and so on. And then the basic premise here that it makes sense to associate some soft modes, some Gaussian modes, with the breaking of conformal symmetry in this. So the symmetry is broken because, well, I put the theory at finite temperature, and there's a conformal anomaly.
Sorry, is this explicit breaking or spontaneous?
It seems like people have different opinions on what you should call this. So the breaking due to considering from finite temperature, I would call spontaneous. But then we will also talk about the conformal anomaly. Yeah. But the point will just be that
It's not a matter of opinion. People have different opinions. You say there's a Gaussian mode.
Uh-huh.
Usually you go more spontaneous breakdown.
Yeah.
So is that what's going on here?
That is something that happens because we're going to be at finite temperature. Yeah. And the mode, so the mode that I'll be concerned with is this reparametrization, F. Okay. And I will try to write down an effective field theory, in a sense, for this mode. And the point of doing that is that I will claim that this is a useful way of organizing some certain calculations. So to be more specific, consider a small reparametrization. And since this is a reparametrization of the coordinates, it acts as a source for the stress tensor in the usual way. And for conformal transformations, you have the usual conserved currents. And the theory that I want to be more specific about is the theory of this mode regarded as some mode that measures the breaking of conformal symmetry and realizes conformal symmetry in a nonlinear way. So from this simple transformation, you can guess or you can see what the effective action for these modes will look like. You get this effective action by integrating out the CFT and writing and obtaining an action for this source itself. So this might be more familiar to you if I remind you of this Polyakov action that's been written down a long time ago, which is essentially defined in the same way, just for a more general metric, which you use to source the stress tensor and then integrate out the theory. So you get a generating functional for stress tensor correlation functions. For instance, another thing that might be familiar to you is this action, which is a particular instance of this Polyakov action that shows up in the context of the path integral quantization of a certain coadjoint orbit of the Virasoro group. So this is to make some contact with things that should be familiar, but I'll be I'll be more pedestrian in that for now I'm only going to need the quadratic action for this small reparametrization. So the quadratic action will be sourced by two insertions of this anti-holomorphic derivative of epsilon, and it is given, or it is determined by the two-point function of the stress tensor. So it's completely universal. And in fact, it is more local than it looks here, because the stress tensor two-point function, if you hit it with one of these anti-holomorphic derivatives, the only thing that survives is a contact term. So you end up with an action that looks like this if you work it out. So it's a quadratic action for this reparametrization. It's a four derivative action, so that's in. Excuse me?
Your formula looks less covariant than the previous one. Go back on this.
Right. Going from here to here, there's a certain ambiguity which is involved, which comes from adding or subtracting contact terms. As we will later see, there's other ways I could write this action. I think what you're after is a more covariant way and form in where.
All I meant really was that if you derive it naively, that detail will actually be zero.
Exactly. So that would be related to this by the addition of some contact terms. And
The whole thing you could call a contact term.
it's true. Okay. If I do what you have in mind and write holomorphic derivatives here, I get an action which I can also use, which will have so there will be an interesting interpretation that has to do with how do I choose the contact terms. Do I write time derivatives here, or spatial derivatives, or holomorphic derivatives? And I'll get back to this, but I can tell you now what's the answer going to be. The answer is that depending how you choose this, it corresponds to, I'm later going to use this action to compute conformal blocks. And there will be different solutions to the conformal Casimir equation with the same eigenvalue. There's a conformal block and a shadow block. And this choice that I make here will determine whether I compute the physical block or the shadow block or a conformal partial wave.
I do want to say that the choice you're making isn't what you get if you actually do the calculation yourself.
Right.
In the calculation you said d bar with the two-point function will be dz cubed with the function, not d tau cubed.
I agree. Okay, so the way I did the calculation going from here to here is by going through Fourier space. But I agree with you that I should have written the action here with holomorphic derivatives, because that's what you get from staring at that. And
You get the d tau cubed.
No, it's q by c is returned d by d tau.
yeah,
It scales differently. Scaling.
there's a temperature here which is hidden. There's a beta which I set to 2 pi. Okay, I'll have to go on to explain the difference between the quadratic actions you could obtain in detail. But I agree it would be more accurate, given what I wrote here, to write holomorphic derivatives here. And that would be just as useful. And the relation between the two has to do with what physics this is going to capture. I'll get back to it, I promise. Okay, there are 4 derivatives, but this should be somewhat familiar if you've seen the quadratic approximation to the Schwarzian action in one lower dimension. Now what you can do is, given this quadratic action, you can invert the kinetic term. You can invert this kernel and obtain the propagator for this mode. And okay, had I written holomorphic derivatives here, you would get something slightly different. But the form I wrote the action this is what you get from inverting the kernel. And again, I'll get back to this to explain in more detail how you should think of this logarithmic term. But the sine squared term looks like, at least naively, like what you would expect for the conformal two-point function of some field with dimension -1. Which makes some sense because this field started, or the derivative of that field was a source to begin with for the stress tensor. So before we understand a bit better how to think about this, let's see what we can do with this, just by analogy to what you can do with the analogous propagator and the Schwarzian action. So if you've worked with the Schwarzian theory, this might look quite familiar because very similar expressions show up there. And then the first thing you can do in that case, you can mimic here almost one-to-one. Namely, you can couple this mode, this mode which is like the source of the stress tensor. You can couple it to two-point functions to define some natural bilinear operators in this theory. And these bilinear operators, you simply obtain them by applying the same reparametrization or small reparametrization to the conformal two-point function of the operators you want to couple to. The expanding out this reparametrization gives you this bilocal operator, which is completely analogous to the Schwarzian case. Now, these are the two simplest things you can do. Of course, now you can go and think about the nonlinear action and nonlinear couplings and so on, but the very simplest thing you can do is this propagator and the quadratic and this coupling, this tree-level type coupling. And that sets up for you some basic Feynman-like rules in this effective field theory of this mode. And the propagator goes like 1 over c. So at large c, there's going to be some perturbation theory you can do by building diagrams using these building blocks. So the very simplest thing you can do is compute a two-point function of these bilinear operators. And that should capture the exchange of a single energy momentum tensor. And of course it does by construction. But so you can reproduce, for instance, the Lyapunov growth of some 4-point function in the out-of-time order configuration from simply computing this 2-point function of bilinears and analytically continuing to the out-of-time order regime. So typically when you take the Euclidean 4-point function and analytically continue to the out-of-time order configuration, there should be some branch cut that you cross. And crossing this branch cut leads to picking up some exponentially growing term. The branch cut in this case is encoded in the log of this 2-point function. Okay. Still questions about this? So, yes, yeah. We'll get there. Yeah. So for now, I'll get to the conformal blocks in more detail in just a minute. But before I do that, let me just mention that there's a generalization to higher dimensions of this story, which is very similar. So in even dimensions, you can define a quadratic action. Again, there's some nonlinear story, but let me just, for simplicity, focus on the quadratic action, which is defined in the same way as before. And the quadratic action involves two insertions of this source, which now comes from a higher dimensional reparametrization. And it's determined by the conformal 2-point function of the stress tensor. So it is still universal, at least the quadratic order, because this 2-point function is. And again, you pick up a contact term as you hit this correlation function of TT with one of the derivatives.
Is epsilon a dynamical field or a classical background?
In this approach, I want to treat it as a dynamical field and study the theory of this mode.
What's confusing
Yeah.
us is that it couples to the divergence of the stress tensor.
Yes.
Which is 0. So you're just talking about contact terms.
It is, yeah.
We don't know how to decide if you're discussing the contact terms correctly.
Why? Because they're ambiguous? Well, I mean, so the
I can rephrase.
I wrote the contact term.
If epsilon is a dynamical field,
Yes.
what's the option from the beginning to get more complicated terms depending on epsilon by n? That's another way of saying that there is an ambiguity in the contact term. But every ambiguity in the contact term can be absorbed in some term in the action. Rewinding what you said, the very first time you said epsilon is another field in the formula.
Mm-hmm.
Why can't you just add to the action something so on that relates to epsilon, which would change some of the answers? Maybe they don't change the singular part that you're interested in, but this is something that needs to be checked.
I think the singular part should be fully determined. So there are other ambiguities that can show up, which would probably come if you do that. Once you invert this action and get the propagator, we will get this propagator in a different way later, and then it will be more clear that there's other terms that could show up, which would be consistent with the symmetries and presumably with the ambiguities in this contact term, but they will not have any physical consequence. If I compute physical correlation functions, these terms will always drop out. I think the same will be true if you modify this in the way you said. So the simplest.
So epsilon is a vector, dimension -1.
Yes. Yeah.
Are you making any assumptions about the CFT? Like CT is
So-
off, for instance, or-
I'm not making any assumptions to write down these things, but in order for them to be useful and to set up this perturbative scheme, I have to make assumptions, in particular large C. So in particular large C, to have a perturbative parameter, yeah, that's the essential assumption.
CT to infinity, then this term dominate or perturbative to one term?
If I take it strictly to infinity, then so large. So I need this. The action is proportional to C, and I need that to be large in order for the perturbation theory involving these guys to be sensible.
So what's the starting point? You start from some conformal field theory, you try to isolate one mode out of the conformal field theory.
I'm trying to understand the stress tensor sector of the conformal field theory.
Conformal field theory is assumed to be unitary. What are you going to assume about it?
Unitary. Yes, I guess. Though
But then there
Um,
cannot be any operator of dimension -1.
well, I will define this operator later in a different way, and then it will be then it will be clear that this is a non-local operator in a sense. So I will later show that you can think of this epsilon as an integral of the stress tensor itself with a suitable kernel. So it's a non-local operator built out of the stress tensor. Yeah. So regarding the ambiguities you were worried about, the first or the simplest one of these when I write this is the fact that modify this scale that shows up here in order to write something sensible in the logarithm. So the reason the scale shows up is simply because you have to regularize expressions like stress tensor two-point functions suitably, as you do when you think about the conformal anomaly. And to make sense of singular expressions like this as well-defined distributions, you have to regularize them. But this scale here is arbitrary. But nevertheless, that doesn't make the physics that this describes arbitrary, because in any physical calculation that you do of reparametrized two-point functions, say, of physical operators, parameters like this will drop out. And there's other similar ambiguities for which the same is true. So I don't think the results you get are ambiguous. So now similarly you can couple these guys to operators by reparametrizing two-point functions in the same way I did it in 2 dimensions. And you can use these ingredients now. The way I wrote it, this was in flat space, but you can again use this to study thermal physics in this case on hyperbolic space, which would be the one you can obtain in a simple way by just doing a conformal transformation. And then study out of time order correlators and so on. But let me not go there right now, because I want to focus on something else and give you a different perspective on how to think about this theory from the point of view of conformal blocks and representation theory. And maybe that will make it a bit more clear how to think about these modes in an unambiguous way. Though if there are more questions, I can try to answer them now. So this divergence of the stress tensor two-point function would just be 0 in odd dimensions. It's related to the absence of the conformal anomaly. So I'm not sure whether there's a story like this in odd dimensions. If there is, it has to be different in some way. All right. In the context of the conformal blocks that I'm about to discuss, you may know that conformal blocks in odd dimensions are much more complicated, or very, very different from ones in even dimensions. Yeah, so I hope that many of the confusions that have been brought up will be cleared up a little bit if I give this different perspective on what this theory describes. So, okay.
Or small departures from thermal equilibrium. And those are usually described like conventional from hydrodynamics, where you say that the temperature is always constant in space, and then you write down equations that govern the current dependence of temperature and heat fluxes.
So I've already argued in the beginning that we can capture the out-of-time order correlation function, the Lyapunov growth, using a single exchange of this mode, which is something that happens way outside of the traditional hydrodynamic regime, in the sense that the exponential growth should be associated with frequencies of order temperature rather than small. Which part? Like, so yeah, why don't I give it a different perspective? Perhaps that will make it more clear. The different perspective on the same theory, which is based on on starting from the external operators that we previously coupled the reparametrization mode to, but instead considering the OPE. Now, I'm sometimes loosely going to refer to a particular term in the OPE associated with some primary O and its descendants as some OPE block. What I mean by that is that it is a sort of half of the more well-defined conformal block that you're familiar with. So in the example of this 4-point function of pairwise equal operators, the conformal block would be the invariant object that encodes exchanges in an OPE sense of some operator O and its descendants. Now, if you want to calculate the conformal block, figure out what is the contribution of some of these operators to the 4-point function, one of the traditional approaches of doing that is by looking at the conformal Casimir equation and noticing that the conformal block associated with the exchange of some operator of dimension delta and spin L should be an eigenfunction of the conformal Casimir with this particular eigenvalue. But then you can see immediately that this Casimir equation has two solutions with the same eigenvalue, one of them being the conformal block we're after, and the other one being some shadow block associated with a shadow dimension delta tilde, which is d minus the original dimension. So the eigenvalue of the conformal Casimir cannot distinguish the two, but the way you should distinguish them, which was also understood a long time ago, is by their short distance behavior. So the short distance behavior in terms of these cross ratios u and v is this particular limit u to 0 and v to 1. And the physical and the shadow block are distinguished by a different scaling in u as you take such a limit. Now, one way to think about the shadow block that I had on the previous slide is as the conformal block associated with the exchange of some shadow operator. And the shadow operator has been defined in this way as an integral over the original operator of dimension delta, where the kernel is given by a conformal 2-point function of the shadow operator itself. So this simply means the 2-point function determined by conformal symmetry associated with some fictitious operator of dimension d minus delta. Now again, this is a non-local operator, so there's no issue with unitarity of the theory. The usefulness of this definition is that you can define a projector, this projector O, onto the conformal multiplet associated with the operator O. The projector is defined in this way, and you can see, thanks to this definition of the shadow operator, I can write a conformally invariant expression that has total weight 0. So the idea would now be that in order to compute the conformal block associated with O, you insert this projector into a 4-point function. So question is, does that work? So you might think that it will work because of the following feature, that if you insert this projector here, you get a part on the right and a part on the left, and each one of these parts looks like two operators on which you act with this projector, and that gives you a conformal integral over the operator that you're exchanging. And this object is manifestly an eigenfunction of the Casimir with the right eigenvalue, because the Casimir that this conformal block should be an eigenfunction of will act on the two operators v and v in this case. But equivalently, you can let it act on the remaining part of the correlation function, which is O tilde. And O tilde is by definition an eigenfunction of the Casimir with the right eigenvalue. So by inserting this projector, we're guaranteed to construct something that has the right eigenvalue under the Casimir. So the question is, does it have the right short distance behavior to be the physical block, not the shadow block? And the answer in general is no. But if you do this procedure of projecting using the shadow operator formalism, you're going to get some combination of the block and the shadow block. It's a very particular combination, but that's not going to be too important. I'm going to refer to this.
Your derivation doesn't make it very clear, but this particular combination is the one that's causing symmetry.
That's correct. Yeah.
Why is it crossing symmetry? It's single valued
It-
symmetry.
That's what I meant to say.
See,
That's what I meant.
yes, single valued. So for that to work, this coefficient here has to have a very particular value, which is not clear from my derivation, but it's also not going to matter for what I'm going to do with it. For us, for now, it's only going to matter that we get both of these contributions. So in addition to doing this projection, you will also have to do this monodromy projection, which is saying that you distinguish these two terms by their short distance behavior and project out the one you don't want. Okay. Now, let me get back to stress tensor physics and consider the stress tensor block. I could more generally consider blocks associated with conserved currents, but let's just focus on this case. And again, this is particularly interesting in ADS CFT or in theories with a gap, because this block is the one that allows you to probe gravitational scattering and bulk locality and things like that. Some of the applications include the case where the external operators are twist operators. Then you get the geometric contributions to entropies, to entanglement entropy. So these are some reasons to focus on this particular block and to consider this formalism that I just described or reviewed for the particular case where the exchanged operator is a stress tensor. Now, the shadow of the stress tensor is defined the way I defined it before, as some integral over the stress tensor itself with an appropriate kernel that's conformal, that's determined by conformal symmetry. But for this particular case of the stress tensor or other conserved currents, you can in fact write the shadow as a total derivative or as a descendant, a symmetric traceless descendant of some vector which involves the original conformal integral. So this K is the appropriate kernel that follows from the definition of the shadow. And this fact that you can write the shadow of the stress tensor as a derivative allows you to further simplify this formalism. So for instance, the 2-point function of T tilde itself is determined by conformal symmetry, of course, but that in turn determines the 2-point function of this field curly E, of which T tilde is a descendant in some sense, or whose derivative is T tilde. And if you work out what this 2-point function has to be, it takes exactly the same form as what we found before for the reparametrization mode. So again, it's a 2-point function that looks like a 2-point function for a dimension -1 vector in this case. And in addition, it has this logarithmic piece. So in the context here, this is simply the object that if you take two derivatives and give it the appropriate symmetries, it reproduces the 2-point function of the stress tensor shadow for you.
Does the logarithm disappear from the 2-point function?
Yeah. So the 2-point function of T tilde is just some, looks almost like the 2-point function of T, just with a different weight in the denominator. yeah, so the log will disappear, and of course this scale mu will also disappear. And again, there's some ambiguities, so you could describe this way. This sort of follows from integrating the two-point function of t tilde twice. So as you do that, you can introduce some integration constants. So there's again some ambiguities that you might be worried about, but these ambiguities are not going to affect any physical object you compute, because to compute some physical correlation function, you always couple this mode to external operators, or it shows up in the OPE. And in the way that happens, any of these ambiguities will always drop out. Or in other words, the object that matters for physical observables is the second derivative of this object. And that will kill any ambiguities. So, okay, so this is the same two-point function we encountered before in this effective theory of reparametrizations. And the claim will now be that it is useful to make this connection and to think of them as describing the same physics. So to test this beyond this two-point function I described, the next simplest thing you can look at are these natural bilinear operators you have in the theory. So previously we had this bilinear operator, which was the reparametrized two-point function of some operators O or V. In this case, the object that this corresponds to is what I called before as the OPE block, which was the stress tensor, which is the exchanged operator, integrated with the appropriate kernel to give it the right conformal properties. And you can show, it's very simple to show that once you write t tilde in this expression as a derivative of some vector, and using the Ward identity in a similar way as I did before, then this expression is exactly the same as that. This?
One before we wrote you do a reparametrization of x by epsilon.
This?
So is this a symmetry of the problem?
What's the symmetry? This transformation?
Yes, reparametrization.
No. So, well, it's a symmetry if epsilon is a conformal killing vector.
I thought you integrate over epsilon.
In
You said that epsilon is a dynamical field.
So in the reparametrization mode story, epsilon started its life as the source for t, and then I integrated out the CFT to get an effective action for this source.
But then epsilon is not a dynamical field. It's a classical source.
It's the
What does it mean to compute the two-point function of the classical source?
so I'm doing a Legendre transform in some sense, in which I trade the stress tensor for this source. Does that make sense? And I know.
I understand what it means to compute the two-point function of the stress tensor.
Uh-huh.
I asked you earlier whether epsilon is a dynamical field or a classical background. Still not
So-
really what the right answer is.
So it starts as a source, as a background, but then I integrate over everything else and study the effective action I obtain this way for that source. Yeah. the same, yeah, it has the same status as the metric in the Polyakov action. Yeah.
The metric,
I assume you're going to say similar.
yes, I think so.
So you'll phrase it better.
Well, I think we're both going to say that Polyakov studied the problem where the metric was dynamic.
Yes,
Because
to
he studied
2D.
several papers. Some of them it was classical and some of them it was dynamic. But I think it was clear in Polyakov's paper which of the two cases he was talking about.
Well, yeah, I'm not, I don't know what's the way I define I don't know what to call it, but was it clear the way how I define it? Was it clear how I define it and that there's an effective action for this mode, and I'm just going to study the physics, but the theory, the action obtained for this mode. Yeah. Uh-huh.
Maybe that's the source of it.
Probably.
One of them is to couple two sources and compute the one PI generated function.
Yeah.
Then you do not integrate it with the source.
Okay.
Not compute correlation function with the source. Another thing is to integrate out a lot of nodes, keeping sub-nodes that you do not integrate out, and you write an effective action for these nodes. Then these are dynamical things that later you should compute correlation function. And my sense is that you were kind of jumping between the two different cases.
Okay. Okay. Maybe.
It's a classical background.
Okay. At least the way this is written, you probably want to call it that. Yeah, but maybe we can talk about the distinction more. I want.
About this formula, because you said that you can verify this explicitly, but on the right hand side, I think you have a. Oh, sorry. I just didn't see that there is absolutely on the right hand side.
Okay. Okay. Yeah. Let me just describe some explicit calculations to you to show why it is useful to rewrite the shadow operator formalism this way. So if you want to compute conformal blocks using this technique, you typically have to do conformal integrals or solve complicated Casimir equations. I'm going to argue that using this technique, it's much easier to compute certain things. Yeah. So for instance, the simplest thing you can compute is simply the two-point function again of these natural bilinear operators. And what you're finding is the conformal partial wave, which was the block plus the shadow block associated with stress tensor exchanges. And using the definition I gave for these B's and the two-point function of that epsilon, you immediately get some answer, which is indeed the conformal partial wave in arbitrary even dimensions. You can check that this compact expression coincides in the dimensions where this object is known. Especially in this Dolan Osborne paper, you can find some expressions to match with. Another thing to mention, and this is going back to the question in the beginning, is that if I use this language I developed in arbitrary dimensions and apply it to the two-dimensional case, then the two-point function of epsilon is going to involve log zz bar. Log x squared is going to be log zz bar. Now, if you use this splitting, which is immediate in 2 dimensions, then these 2 terms give you different contributions to the 4-point function, or to this 2-point function of bilinears. Namely, the log z part has precisely the right monodromy to give you the physical block, whereas the log z bar part ends up giving you the shadow block. So something nice you can do is do this monodromy projection from the outset. So you can do the monodromy projection at the level of this 2-point function by just dropping the piece with the wrong monodromy, and you're guaranteed that what you compute later is always going to be physical blocks. In more complicated calculations, this is going to be very useful, because you will not have to do this monodromy projection at the end. Okay. So here's a brief summary of what I've did so far. I described to you this reparametrization mode theory, which is a way to think about the shadow operator formalism for stress tensor exchanges. And so far, I've just argued that this is useful to compute certain things, certain conformal blocks, because calculations are more local. You're just doing some effective field theory calculation, some exchanges of this mode, but you don't have to do any conformal integrals or hypergeometric sums or solve Casimir equations. Certain things are very simple. In addition, you can do the monodromy projection at the very beginning. So here are some examples for how this works. So in 2 dimensions, what's more interesting than these global blocks that I described so far would be Virasoro blocks, where you have more than just a single stress tensor exchange. These Virasoro blocks are known in certain regimes. So in particular, in the case where, let me talk about the 4-point function for now. So in the case where all 4 operators are light compared to the central charge, have small dimensions compared to C, and in the regime where 2 of them have dimensions of order the central charge. Now, oops. Kotler and Jensen used this theory that I described to reproduce these results in a very simple way. So it's simpler than other ways you can get these. And it's now very clear why this works, because if you use the reparametrization modes to compute higher order contributions, so higher order diagrams where you exchange multiple of these modes, you're at the end of the day just doing the OPE in the shadow operator formalism. So for example, in this regime where all 4 operators are light, so there's some parameter which is of order 1, the dominant diagrams in this theory of this epsilon mode are just ladders. And these are almost trivial to compute. This one is the one I talked about at length, and these are just powers of the same object. So the exponentiation of this block in the Virasoro case follows in 2 lines. Now, more interestingly, you can study this heavy light block, which is also known in closed form. You can take this closed form expression and expand it in 2 parameters. So one parameter being the heavy dimension divided by C, which is some order 1 parameter in this setup, and the other parameter being the light dimension. This double expansion takes some form, and you can associate to every term in this expansion a particular diagram where these red lines are always epsilon exchanges. So here something new shows up, which is the cubic self-interaction that's going to follow from the cubic action. That I'll get back to that, but it's defined the same way I got the quadratic action before, just the next order. So you can understand this heavy light block in some Feynman diagram way. Now, why is this useful? Well, it might be useful because the question has come up recently in these papers whether the heavy light block in higher dimensions has similar features as in 2 dimensions, in particular whether it exponentiates. Yeah.
So when you ask this question parity, do you mean this kind of similar approach where you try to some contributions of stress tensor multitrace?
Exactly. Yeah, what they do in these papers is consider multi-stress tensor exchanges, but in some particular light-cone limit. There's some.
So this is not a question about the conformal.
Why not? Yeah.
Because a conformal book in higher dimensions just counts exchange of one operator. I can write it down in 4D and
Okay.
look at it and tell you whether it's exponentiates or not, because it's like coherent functions.
Right. So this is about multi-stress tensor exchanges of some particular type that I don't have time to explain, but a particular class of multi-stress tensor exchanges. And the question is, if you sum them up, do they have some similar feature as the 2D heavy light block? In particular, do they exponentiate? And yeah, something I'm looking into is whether you can use this approach, because the way this is written, this diagrammatics is almost identical in higher dimensions. The step going from 2 to higher dimensions is almost immediate.
But also in higher dimensions, it's not universal.
Right. So I said a particular subset of multi-stress tensor exchanges. The particular subset is precisely such that you do get something universal. I'll be happy to talk more about it later. But
Exponentiation for a light open function and this parity?
I think using this logic, it follows. Though I can't point you at any particular reference right now. Yeah. Okay, let me use 2 minutes at least to talk about a higher point case, so where this formalism becomes quite powerful to get to not just reproduce these things, but get some new results. So you might be interested in higher point blocks for various reasons. So you can higher point out of time autocorrelator. So if you have access to higher point blocks with 2 heavy insertions, you can probe things like the ETH statement for higher point functions. Entanglement entropy for multiple intervals and so on. So there's reasons to study the analog of the identity block in higher for more insertions. So as an example, let me talk about 6 insertions of, again, pairwise equal operators. And I'm interested in generalizations of the identity block. Now there's 2 different channels I can think of. This one Vladimir studied 2 years ago. He called this the comp channel and understood it in quite some detail. I'm going to give as an example this channel, which is really purely gravitational in the sense that you're just exchanging stress tensors, and it's sensitive to the stress tensor 3-point function. Now again, you can use this formalism to show that these different channels are in one-to-one correspondence with diagrams in this theory of this reparametrization mode. In particular, this example I want to discuss involves the 3-point function of this mode. Now, how do you get the 3-point function? One way would be to write down the cubic action. But it turns out to be complicated. There's a much simpler way, which is just taking this realization that the derivative of this mode is the stress tensor shadow. So you can relate that mode to the stress tensor itself and write down relations between derivatives of correlation functions of that mode and correlation functions of the stress tensor. And these relations are pretty much trivial to solve and give you immediately the 3-point function that you need in a diagram like this. The only thing to take away maybe is that this 3-point function now doesn't contain logarithms but dilogarithms. And this propagates into the solution. So this global identity 6-point block, which is just given by the 3-point function of reparametrized 2-point functions, takes a form like this. So the details don't matter so much, but the dilogarithms propagate through. So there's some interesting transcendentality and some interesting branch cut structure in these blocks, which has consequences if you now study out of time autocorrelators, where you analytically continue across these branch cuts and so on. So by understanding such blocks, you can classify what happens, or what's the time dependence of higher point out of time autocorrelators as one example. Another thing you can show immediately is that this thing exponentiates in the case where all the external operators are light.
Can you also fix the numerical coefficient being found with the right hand?
That's fixed, yeah. I'm just not writing it here. So there's some number here, but then it goes like the dimensions over c squared. That's the leading term. And it's, in a sense, it's the fully connected term, which is, yeah. Okay, maybe I'll skip my remarks on thinking about this as an effective field theory of chaos in thermal states, because I'm out of time. Can ask me about it if you're interested. So so I tried to explain how it is useful to think about some effective field theory for these reparametrization modes and how this is connected with the OPE and the shadow operator formalism that's used to compute Euclidean blocks. And then you can apply that, and it becomes a powerful formalism once you do more complicated things such as heavy Virasoro blocks or quantum corrections to such blocks or higher point blocks. Then calculations are much simpler if you do this. Okay, here are some questions, but I'm out of time, so I'll just leave it up there. Thank you.